obviously, so you're just left with 2 pi. Well, e to the 2 pi I is just plus 1, right? So you've gone one full wavelength, you've gone one full cycle of your waving motion, if you see what I mean. Now, alternatively, you could be in any fixed point x, doesn't really matter where it is, and you just wait. So imagine you start at time little t here 0, and then the waving's continuing. Everything's waving, and little t time later equal to the period, big T of the wave. That's 1 over the frequency. Well, the frequency is 1 over the period. So when this little t becomes big T, the t's cancel. Again, you get e to the I 2 pi. So again, that's just one cycle. So this waveform here has the correct properties to describe a waving motion, right? Both relative, with respect to distance. As you move along a full wavelength, you've gone one full up and down cycle. One cycle, one wave. And if you wait time period, well, you're at a fixed point here, then the wave will have completed one cycle at a fixed point, just going through time. So your wave function, this describes the waving motion. It depends on the position x and the time t. So psi is a function of x and t. Okay, so all right. Okay, well now it's just calculus. We've done this before. So d psi by dt. Just differentiate this with respect to time, and you'll get this. The minus I omega. So 2 pi over t is just 2 pi f, which is omega, so you get minus I omega psi, right? Now, if I multiply both sides by IH bar, why do I do that? Well, because, therefore, IH bar d psi dt equals IH bar times this, which gives you h bar omega e, psi, sorry. Now h bar omega, where is that? Here. So we just put an e here. Okay, so we put an e here, there. So it equals e psi, right? So this term here equals e psi, right? Now why am I? If I multiply both sides by psi. Okay. So E psi we now have. E psi, it's this. Okay. Now let's try to find p squared over 2m times psi. So where are we? P squared over 2m times psi. Well, p squared from the de Broglie relation is this. P squared is just h bar squared k squared. Right, from here, so you've got that, but this k squared psi, if you differentiate this psi function with respect to x twice, so 2 pi over lambda is k, right? So you've got kx here. So you differentiate it twice, you'll get you'll get this. Okay? If you differentiate it twice, you'll get a k squared coming out here, but h bar squared k squared is p squared, right? Okay, so this is what? So you now got a value for p squared over 2m psi. P squared over 2m psi. And this v psi doesn't change, just leave it there. Alright, now e psi equals p squared over 2m psi plus v psi. Now you've got a term for e psi. Here it is. Okay, so just plug this in for here. P squared over 2m psi. P squared over 2m psi is this, so just plug it in. Okay. Plus v psi, which is just here, no change. Okay. Right, so now we have our new form of the Schrödinger equation, now with 3 terms, right? So this is the form of Schrödinger's equation that we will use for this, the next 4 chapters. Big, more than a third of the whole textbook, right? So Schrödinger's equation is very, very important in quantum mechanics. And there's a whole branch of quantum mechanics called wave mechanics, which, like I said before, essentially is just the branch of quantum mechanics that deals with solving Schrödinger's equation. It's usually shortened to just wave mechanics, because you're talking about the wave function, this function psi here, right? So here's the Schrödinger equation in the form that from now on we will use. Okay. Now now let's start talking about this potential V. It's a potential energy. Let's start giving it some properties. Start at sort of a high level, and then become more and more concrete, more specific in different circumstances. But let's say this potential energy term here is independent of the time. Let's say it does not change with time. Okay. Now this wave function here, you just look at it, is a function of position and time, x and t. Right? Said that before. So I mean, you could have a potential. Well, just call it potential. It's sort of easier rather than potential energy all the time. This potential term V could be both a function of position and time, but let's talk about those cases where the potential energy does not change with time. Okay, so in other words, it's only a function of position. Right, so it's v of x. Now, if that's the case, then you can split up, in a manner of speaking, this psi function into 2 terms. So the product of 2 terms. So in general, your psi functions is a function of, in mathematical sense, it's a function of position x and time t. Right? Now you can rewrite that as the product of 2 functions, u of x and f of t. Now the u of x, that's just the spatial part of your psi, and the f of t, that's the time part of your function psi. Okay, so so long as your v here does not depend on time, so it depends only on x, then you can split up this psi function into the product of two other functions. One function depends only on x, and the other one depends only on time. Okay, so u of x, f of t. All right. So take this product function, this u f, and plug it into the Schrödinger equation, our new form with the potential term v. Right. So just take this u f and put it here, here, and here. Okay. Do it for homework, and get your result, and then divide left and right hand side. So divide both sides by psi. In other words, uf. Okay. I'll just say that again quickly. Substitute for psi. Instead of psi, put the uf, because it's the same thing, right? Put uf here, and then divide the result by uf. Now, if you do that, you will end up with something like this, right? Because things like there's no f here, right? That cancelled. And here we've got the potential now depends only on the x, right? The position, not on time. That was the assumption, right? And over here, the u's disappeared, right? Because the f depends only on time, not on position. Okay. Now have a look at this. Now, do this for homework. Just get out your pad and pencil and just substitute the UF into your Schrodinger equation here. Then divide the whole thing by UF. You'll get this, right? So do that. And now have a look at it. The left-hand side here, that depends only on x, only on position, right? But the right-hand side depends only on time, right? I mean, these are all time function things on the right-hand side. And on the left, they're all spatial, x type things. And yet they're equal. These two expressions are equal. Now, there's only one way that, I mean, the x and t, they're totally independent things, right? So there's only one way that those two sides, left-hand side and right-hand side, can be equal, and that is if they are both, in other words, the left-hand side and the right-hand side, are both equal to a constant. It's the only way it's possible, right? So that means the left-hand side, which is this, is equal to the right-hand side, which is this, function of t, function of x. Okay, the only way that can be possible is that both of them, left-hand side and the right-hand side, are constant. So let's call that constant e, or it could be c or k or anything. But anyway, just call it e for reasons you'll become clear next session. In fact, down the bottom here is a clue. So we'll just call this constant e, right? So that means this same thing is just e, the constant e, right? So we can rewrite this now. So if we let this left-hand side here equal e, so instead of having this, we could just put where my hand is. We could just put e here. Okay. So the u would go up, multiply both sides by u, so you'll get eu. Okay. So this becomes this. Okay. Now we have, now remember, this potential is only a function of x. U's a function of x, right? Down here, u's a function of x. So this whole equation here now is only about x, position. So this is a position type equation, right? Now we can take this equation and rewrite it slightly. So we take the u outside of the brackets. So we now have this term inside the brackets times u equals a constant times u. Now this term in the bracket it's a differential operator. Right? Now what's an operator? Well, go back to the previous course on finite group theory. An operator is, well, generally speaking, it's just a symbol that instructs you to do something. Like, well, for the simplest one, I suppose, a kindergarten kid would know, is this. If you see this symbol, just plus, it's telling you, it's instructing you to add two numbers, two matrices, or whatever. Okay? And this symbol, instructs you to multiply. Well, in this case, this operator is instructing you to differentiate twice with respect to x, d squared, dx squared, plus a term, and add